this talk will concern a very specific question. Is the MUB question in dimension 6? We have heard about this before. And so basically, I'm only considering this single question in my talk. This is something I've tried to solve for at least 15 years, and I'm very stubborn. Maybe I'm not very clever, but I'm very stubborn, and I'm still trying to solve it with new and new ideas. And we will see how many failures we have had so far, and whether this new approach will lead to success is a question. Okay, so what do I do?
On the side of the switch, you have to be green.
Oh. And now? Yeah, so I should say it's work in progress, and maybe I should mention my colleagues, Mihály Weiner, who was speaking an hour ago, and Daniel Varga and Ákos Macangos. And as it says, it's work in progress, or another attempt and possibly another failure to prove the non-existence of full sets of 7 MUBs in dimension 6. So I think maybe everyone in the room now knows what MUBs are, but anyway, Mihály started his talk by saying everyone knows what MUBs are, but I'd rather say that so you have mutual unbiased basis, which means you have 2 orthogonal bases being unbiased to each other if any 2 vectors coming from different bases have the same point. Here. So if they have the same angle between them, so to speak, so the scalar product is the same. And in this case, of course, we heard it many times that if you take these scalar products x, y, yj, they make a matrix, and if you renormalize them with square root of d, then you get a complex Hadamard matrix, which is basically a square root of d times a unitary matrix. These normalizing factors will appear throughout the talk, and I hope I got it everywhere right, but if not, please correct me. So the 2 theorems we heard is that for any dimension, we get at most d+1 such orthonormal bases, which are pairwise mutually unbiased, so every basis is unbiased to every other. And of course, we also heard that such a construction exists. A full set of MUBs exists if the dimension is a prime power. And of course, the first outstanding dimension is dimension 6, which is the first non-prime power case. And the question is, what is the maximum number of MUBs in dimension 6? And the conjecture of Zauner, I think from 1999, says that upon numerical evidence, this maximum number should be 3 instead of 7. So 7 would be a complete system, but he conjectured there is only 3. And ever since there has been lots of numerical evidence supporting this conjecture. So I'm not so ambitious to prove that there are only 3, but let's at least try to prove that there aren't 7 mutually unbiased bases. So of course, what are the connections? We also heard this connection, but let me go through it. That once you have MUBs, then you can have several pictures in your mind. Probably the easiest picture is to think of each basis as a unitary matrix, so to speak, and then these transition matrices are complex Hadamard matrices. So if you have this image in your mind, then you are thinking of the unitary group, and you have d+1 points in the unitary group, which are arranged in a very special configuration in such a way that these transition matrices are always complex Hadamard matrices. Another way to think of it is to introduce coordinates with respect to some basis, let's say x node, and then we get the identity matrix here, and then, as we said before, we have complex Hadamard matrices. And so these are the unitaries with each age being a complex Hadamard matrix. And then, of course, the transition matrices should also be a complex Hadamard. And in this case, if you have this formalism in mind, then you can think of the columns of the matrix as vectors. And this was also mentioned in Mihai's talk, that you can think of such a vector as an element in the group T to the D, where T stands for the unit circle. So you take the complex unit circle, you take its d-dimensional power, it's an abelian group, and you can now think of a complete set of MUBs as a full set. Sorry, a full set of MUBs can be thought of as a special configuration of d-square elements in this group. Why d-squared? Well, because the first basis became the identity, so that's not in your torus. So only the last d basis became unit vectors in this torus. So altogether you get d-squared elements. And you already see that we lost a bit of symmetry here. So in this arrangement, when you think of the unitary groups, then nothing is special. Every d+1 basis has the same role. In this case, we already lost symmetry because we made coordinates with respect to one basis. So this might not be such a good idea, but on the other hand, we go down to a simple abelian group. And so I summarize in the first part of my talk, I try to summarize previous attempts in the last 15 years, how we try to solve this, how we try to prove non-existence of 7 bases in dimension 6. The first attempt is a very natural one. Well, I repeat these 2 lines so that you don't have to remember from the previous slide. So once again, you have the identity matrix and the complex Hadamard matrices. And the first very natural attempt, if we had some simple analytic classification of all complex Hadamard matrices of order 6, then we could just plug in that classification to H1, and then you do some computer algebra, and hopefully the computer just spits out the result that, okay, this cannot be completed to a full set of MUBs. Unfortunately, the state of the art is that Ferry-Sörlősi constructed a 4-parameter family of complex Hadamards of order 6, which is conjectured to be complete or almost complete. But still, the construction is not given by closed formulas. And when you try to plug that in for H1, then the computer algebra just blows up the memory, as testified by Marcus Grasser.
So, but this is not complete in a sense. There is this singular point of tau.
Sure,
and the person do not know whether there might be tau, prime tau, double prime, and so on.
Yes, exactly. I didn't want to mention it, but yes. So it's conjectured to be sort of complete with possible exceptions. Now, of course, the possible exceptions may exactly lead to the full set of MUBs. So we are in this approach, we are pretty far from the solution because we do not have a full classification, and even what we have does not give the computer with the computer algebra does not give the result. Yeah.
For Marcus, probably could you carry through the continuous parameters which in your computer algebra which come in these families, or is that the repeating element as well?
Say the recipe works very well. If you specify the 4 parameters, then you can solve, or you will find that you get in an exceptional point, or that the solution does not give you modulus 1 for the other variables. That's kind of easy. So in that sense, you can apply the recipe. But if you want to get the structural information, then you just leave the 4 parameters as free variables. And if you try that, at least I have not found a good ordering for the Gröbner basis or things like that, that you get the full picture. It's not excluded that, and I'm still hoping that I find a way, but currently, 1 terabyte of memory is not enough.
Right. So there are 2 problems, as you see. First, even if you could do it, you would still have to prove that this parametrization of Ferry-Sörlősi basically gives the full set of Hadamards, which is probably close to the truth, but we can hardly exclude exceptional points and so on. But nevertheless, let me make a remark here, which will be used later. There are some nice families given by closed formulas. For example, the two-parameter Fourier family, FAB, which contains the discrete Fourier transform matrix, F6, and another two-parameter family also found by Ferry-Söllershi, found by a block circulant construction. Those are nicely given, and I guess if you run your computer, it will say that they cannot be extended to a full set of MUBs. But exactly, I just wanted to say the next sentence that we don't need to run the computers because we have such results already, but I will mention it in this slide. So the next attempt, which I had again, I don't know, 13, 14, whatever years ago, is a very natural attempt again. It's not really it's not good mathematics. It's just you want to decide this problem, yes or no, do it by discretization. You see, we agreed that the vectors of the Hadamard matrices can be thought of as vectors in the torus. So each of oh, it's not listed anymore, but so each of them has modulus 1, right? And complex numbers. So if they have modulus 1, I can I can just pick a large n, say 100 or 1,000, whatever, and approximate each entry in each Hadamard matrix by nth roots of unity. And then this is going to be a finite set. And if I somehow I'm able to show that all of these sets are very far from being a full set of MUBs, then a full set cannot exist, because obviously if it existed, then one of these approximation systems would be close to it. So if all of them are far, then a complete set cannot exist. Of course, you may object that if n is 1,000, then we have so many variables that there is no way we can carry out this. Even though it's a finite problem, we just cannot get to the end of it, and that's exactly the problem. So I said that the advantage is that the problem becomes finite, and there is a side result, namely if H1 comes from this Fourier family FAB, then it cannot be extended to 4 MUBs. So you don't have to run your computer because we have done it already, although with this discretization scheme, and we see that it cannot be extended not only to a full set, but also to 4 MUBs. The disadvantages are obvious. This would be a very ugly proof, and we would learn nothing from it more than the answer, whether it exists or it doesn't. And also, the other problem is what I mentioned, that you need meticulous error estimates, how far you need to be from the full set of MUBs, and the running time is close to infinity, so we could never get to the end of it. So we basically abandoned it, and we had another idea. Why not try to do some harmonic analysis, basically Fourier analysis, but I didn't want to use the Fourier because I'm using it for the Fourier family, Fourier matrix. So I say harmonic analysis on the abelian group torus to the D. This is possible because, as we said before, each column of the Hadamard matrices can be thought of as an element in the torus to the D. And once you are in that group, you can try to perform some harmonic analysis, and very nice, very simple, very nice ideas. And amazingly, it gives easy classification of full sets of MUBs in all dimensions up to 5, 2, 3, 4, 5. And it also gives, with a further idea, and in a joint work with Mihai Weiner, it also gives a very nice analytic proof of the fact which I mentioned earlier, that any matrix from FAB cannot be extended to a full set of 7 MUBs. So in a way, the analytic proof that we give with this nice Fourier analysis is much weaker than the discretization approach that we got in the previous slide.
You could extend it to the set of 4 bases?
Pardon?
Is it likely that we could?
No, we cannot extend it by a computer discretization. We already proved that. But nevertheless, we wanted to make a proper mathematical proof, which a human readable proof, yes, which you can actually convince yourself that it's true. So this is a weaker result, but it's a nice mathematics. And the disadvantage is somehow, amazingly, it breaks down for D equals 6, 7, 8, whatever. And here I must mention that it looks like the problem with this approach is amazingly not that 6 is not a prime power, it's just simply too large. As the numbers become large, there are more more freedom of variables. And while everything happens nicely for 2, 3, 5, 4, and 5, it just breaks down for 6 and also breaks down for 7, although it's a prime number. Nevertheless, the method just breaks down. So we also abandoned or partly abandoned this method. And then we thought, okay, why don't we go back to the picture of unitary groups when you try to select a special arrangement of d+1 elements in the unitary group. And we had a harmonic analysis on the unitary group, basically meaning that some functions turn out to be positive definite on the unitary group, and then you can somehow perform Delsart's method in a non-commutative setting and arrive to the same bound again as always, that you cannot have more than d+1 MUB in any dimension d. But somehow in the proof we cannot make a difference between dimensions, whether it's dimension 6, 7, 11, 12. Everything seems the same, and indeed it turns out a very recent result. Someone by these authors, they basically prove that this method cannot possibly work. You cannot ever get a better bound than d+1 with this method. So basically we have to abandon that as well. And so now we are down to lots of failures, exactly, and we are down to the next possible failure. The second part of my talk is what we are trying to do now. Yeah, maybe God is saying, well, why don't you look for the bloody? Yeah. It exists. Maybe it exists. Yes, but many people try to find it by computer, and well, we just cannot. So the current attempt is based on MUB-triplets, because the idea is very simple. The 7 MUBs, a full set of MUBs, they are conjectures not to exist. It's very hard to find something which is not to exist and very hard to prove that they don't exist. But what is the last thing that actually exists? Well, MUB-triplets, they exist. And in fact, they exist, and there is a 2-parameter family of MUB-triplets also found by Ferry-Sörlősi, generalizing an earlier construction by Zauner. So it's a 2-parameter family of MUB-triplets. And by computer search, we are quite convinced that there are no further MUB-triplets. So this would be a sort of a reasonable approach to say, look, complex Hadamard matrices are too hard to classify because they make a 4-parameter family and we don't get closed algebraic formulas, memory blows up and so on. But actually, MUB-triplets seem to be only a 2-parameter family and given by fairly nice formulas. And so why don't we try to say that, okay, these are the only MUB-triplets. If this is true, then also the construction of Ferry-Sörlősi leads to, so the first matrix comes from a block circulant family, but the second matrix, which is the identity, first matrix is block circulant, the third matrix in the triplet is always in the Fourier family. So once you have anyone in the Fourier family, we have the result already that it cannot be extended to a full set, or it cannot even be extended to a fourth MUB-triplet. So this is a reasonable approach, and it would lead to complete success. So what about MUB-triplets? How can we possibly characterize them? What is the idea? So suppose that these 3 ONBs, orthonormal bases X, Y, and Z, they form an MUB-triplet. And as mentioned by Mihai and also by Gerhard Zauner previously, we can, instead of vectors, we can always think of one-dimensional projections. So instead of, I'm using the physicist notation again, so that instead of a vector x xi in the orthonormal basis x, I take the projection onto the one-dimensional line spanned by xi. And so with qj and rk corresponding to x, y, and z, the orthonormal basis. And then the one advantage is that any phase factor will cancel out. So if I think of a concrete vector, I can multiply it with a phase factor, but the projection remains the same. And also we have that these operators, when you have two MUBs, you have these operators Pi, Qj, they form an orthonormal basis in the space of D by D matrices. Of course, you have to normalize, I think, by root D with respect to the Hilbert-Schmidt inner product. And I wrote out the proof, which is pretty simple. It becomes 0 because of orthogonality, and if the indices are the same, it becomes 1 over D if the indices are the same because of unbiasedness. You see, here comes the unbiasedness condition that xy squared is 1 over D. So they make an orthonormal basis in the set of matrices, so we can somehow try to use them. So how? So we are building now a Hadamard cube from MUB-triplets. So given an MUB-triplet, we associate a cube, a D by D by D cube, which I call C tilde because I will have to renormalize it. So C tilde is given by coefficients at position I, j, k. I'm taking the trace of Pi, Qj, Rk. And if you write it out in physics notation, I put the Pi, Qj, and Rk for you. And of course, the trace you can circulantly pull over the xi to the other side, and it becomes xi, yj, zk, zk, xi. So if you like to think of in terms of vectors, you can do that. If you like to think of in terms of projectors, you can do that. And in this way, you have an object, which is a three-dimensional object, a cube. And we are now trying to establish what properties this Hadamard cube. Okay, I'm calling Hadamard cube C the renormalized version, because you see, what is the absolute value of this product? Well, each of them has absolute value 1 over root D. So altogether, it's 1 over D to the 3/2. So if I want absolute value 1, I renormalize by D to the 3/2. So I renormalize my cube, and I'm trying to establish the property. First property is that all entries of the cube have modulus 1, I just said it, and all two-dimensional slices are complex Hadamard matrices. I just list up the properties, and we will have some nice picture generated by Mishi, which I'll show you. All one-dimensional lines sum up to root D, and parallel slices are phase equivalent to each other, meaning that one is obtained from the other by multiplying the rows and columns by appropriate phases. And let me try to. Yeah, so here is the cube, and this is what it means, that each two-dimensional slice is a complex Hadamard matrix. Anywhere you slice in any direction. This is also a,
like Rubik's cube.
well, it's a Rubik cube, but it's 3 by 3 by 3, but actually 6 by 6 by 6. You should imagine, of course, but in the picture it's only 3 by 3. So these two are equivalent. Any parallel slices are equivalent to each other, and phase equivalent. No, sorry. Yeah, so there is I didn't define. So equivalence is a relation on complex Hadamard matrices, but I try to define phase equivalent, which really means that if you start from the green one, then you can multiply its rows by some phases and its columns by some phases, and you get the brown one.
You are allowed to exchange two phases. Exchange two phases, no.
Well, permutations of the rows is not allowed. Only phasing. That's why I'm saying it's phase equivalent. But you are in the cube. You are free to change two slices because it only corresponds to changing, relabeling your projections in the origin. And this is the property when I said that you take a one-dimensional line. It just means that you pick any direction from the 3 directions, and you cut your cube through, and like that. And the sum of the elements must be exactly root n, not only in absolute value, but exactly root n in that line. Yes. And you may want to change your direction, choose another line.
Complex numbers have to be real.
Exactly, they are complex numbers, but they all add up to root n. So it's like a magic cube, really. All slices are Hadamard, parallel slices are equivalent, all one-dimensional stabs are adding up to root n, and this is something for the later part of it. So these are the nice properties, and actually I wanted to convince you that this is true. I mean, why is this true? All of them have modulus 1. This was obvious. And if you fix one index, so you take a slice, let's say you fix I, and you run with j and k, then what happens? This is a Hadamard matrix, a complex Hadamard matrix, and it is multiplied. This will just multiply the rows, and this will multiply the columns. So you get just phase factors multiplying the transition matrix. This was the original transition matrix between the vectors y's and z's, and then you are just applying phase factors. So that's why parallel slices are equivalent. Why do the one-dimensional slabs or stabs they sum up to root d? This is a nice trick, because you see any basis, you know, the projections in any basis, they sum up to identity. So if you fix I and j and you sum up for k, which is exactly when you stab your cube vertically, then what do you get? You make a summation over k, but that means that you sum over k is just the identity. So basically you get trace of piqj. But if you calculate piqj trace, you just get 1 over d. So finally you get root d. So it's a very simple trick, but nevertheless, you may agree that it's very nice properties of the Hadamard matrix. And
And such a cubes exist for what dimension?
Good question. I will just mention it right now. So some obvious questions arise immediately. Do these properties imply each other? Maybe some of them are superfluous. And I'm telling you, mostly they are independent, because 1 and 3 do not imply 2, meaning that even if I tell you that you have all slices being Hadamard matrices and they are phase equivalent, it nevertheless doesn't guarantee that they sum up to root n. You can imagine why, although it's a nice construction, that in fact you can make such cubes with a very simple construction which resemble this cube in a way. You take any 3 Hadamard matrices, H1, H2, H3, and you make a cube by the same trick. H1 at ij, H2 at jk times hk at h3 at ki. You define this cube, you will see that the slices are Hadamards, they are phase equivalent, but of course there is nothing to guarantee that they add up to root n. Because, well, if I may go back, what was so here at the end we used unbiasedness. If there is no unbiasedness, there is nothing to guarantee that they add up, right? The other may be more surprising, that even if you fulfill 1 and 2, they may not imply 3, because we have computer counterexamples in dimension 4. So even if we agree that all slices must be Hadamard and all one-dimensional stabs add up to root d, unfortunately, some slices might not be equivalent parallel slices in dimension 4. However, when we search for numerical evidence in dimension 6, it looks like 1 plus 2 implies 3, which may help later on, that we don't, in dimension 6, we don't need to specify 3. It just comes for free from 1 and 2. And I want to mention 2 results, which is mathematics, because so far I told you ideas and whatever, but we have two nice results concerning the cube. One is another natural question that comes up. Suppose you have a MUB-triplet here, I have an MUB-triplet there. You construct your cube, I construct my cube, and they are the same cubes. Is it true that we started from the same triplets? First of all, what does it mean, the same triplets? In that case, same means unitary equivalence, that my triplet can be carried over with a unitary equivalence to your triplet. And indeed, this is the theorem. If you have two MUB-triplets which generate the same cube, then they are necessarily unitary equivalent. And basically, the proof is the proof is a nice idea of say, we define a mapping on the space of matrices by mapping PIQJ to P tilde IQ tilde J. And we extend this linearly, and we claim that this happens to be a star algebra isomorphism. And if it is, then we know that it's a general theorem that all star algebra isomorphisms on the space of matrices are given by unitary equivalence. And how do we prove that this is a star algebra isomorphism? Well, basically, you need to see that that it preserves the products. And for such a product, it can be expanded in the basis. We all agree that these matrices are an orthonormal basis in the space of matrices. So you might try to expand this product in this basis, and you might try to do the same thing with tildes, and you hope that the coefficients will be exactly the same. And the reason why they are exactly the same is that when you do such an expansion, then it can be done with the entries of the cube. So if you have the same cube, then you will have the same coefficients. So finally, you get that it preserves products. And so it's given by a unitary equivalence. So that's one nice question. And the other question is, can you reconstruct? So if I give you a cube with all properties 1, 2, and 3, I'm asking you, please give me an MUB-triplet which gives you this cube. From the uniqueness theorem, we know that such a triplet is basically unique up to unitary equivalence. But can you really construct one? And the answer is yes, you can, because it's pretty simple. Because you can always say that in an MUB-triplet, the first basis could be taken as the standard basis with identity matrix. The second basis, you can see from the construction that basically you take the first horizontal slice in your cube. That will be your second matrix, which is unbiased to the first. But what is going to be the third? And the third one, quite nicely, these PIQJ, they form an orthogonal basis. And actually, the coefficients of any RK, when you expand in this basis, is exactly the trace of PQ star RK, which is the Hilbert-Schmidt product. But when you look at it, it's just the conjugates of the elements in the cube. So basically, you can reconstruct RK from the coefficients in this basis. So from your cube, you can simply define RK. Okay, it's one thing to define RK, but then you hope that it's a one-dimensional projection, and they are orthogonal for K and K prime, different indexes, they are orthogonal, and that they generate the cube. And you can all prove that because, well, you need to prove what? One-dimensional projections corresponding to an OMB. So one-dimensional, the trace must be 1, R squared must be R, and R star must be R. And they are orthogonal so that the trace of any two different is 0. And when you try to calculate such a thing, that R squared equals RK, then you run into a lot of troubles, because when you square such an expression, then you get quadruple products here. And you have to show that on the other side there are only quadratic products. How could possibly that happen? And I'll show you, because it's better to show not the whole calculations, but things like during the calculations, things like these huge sums appear. On the left-hand side, you have a summation of 5 different cube elements. Some of them conjugated, some of them not. And what you do is at this point, you use the equivalence of horizontal slices in the following manner. That, okay, so whenever someone is conjugated, it will be denoted by yellow, and then someone is blue, it means it's not conjugated. So you see that the first 4 terms are vertices of such a rectangle. And this is exactly, so back to Rob's talk, who was talking about 2x2 submatrices. When you take a 2x2 submatrix, this is exactly the so-called Hagerup invariant that you multiply 2 diagonal vertices with conjugation and 2 without conjugation. And there is yet another somewhere in the cube. Not exactly somewhere, because exactly on the vertical line. And what you do is, by equivalence, the thing is, because slices are equivalent to each other, the Hagerup invariant does not change. So you can move up, and the Hagerup invariant doesn't change. And when you move to the level, then they cancel each other out, because this guy was multiplied once with its conjugate and once with itself, so it's just 1. So instead of this five-term product, you will get a 3-term product. And once you get a 3-term product, it breaks up to a summation of well, the summation of the 3-term product simply breaks up, and finally you get exactly the answer that you are looking for. So that is behind the proof of the reconstruction theorem. And I think I'm basically at the end of the talk. Is just, let me just say what the plan is, because it's very nice we have reconstruction and uniqueness and everything, but what is the plan to prove the non-existence? The plan is the following. So from a MUB triplet, we define a Hadamard cube, and we can think of the cube C as 216 variables, satisfying a lot of constraints. Yeah, there are lots of constraints. And it could be that, well, these properties can be listed as polynomial equalities, right? From the variables. And what we hope is that these polynomial equalities may imply some non-trivial, so that's where I suggested to Marcus that, okay, we switch on the computer algebra, and there is, on the left-hand side is a huge list of variables and equations, and we are trying to prove something on the right-hand side, which is a single polynomial equation, which is somehow non-trivial. And the non-trivial equations we should be able to prove, after this being satisfied, that one facet of the cube must belong to the Fourier family. If this is the case, then we are done, or not. And that's the end of the talk.